going to do quite a lot today, I hope. Before I get started, officer is going to have to be cancelled today because I have a committee meeting that I have to be at, and 10 o'clock is when they're having it. And so if you need extra help or you have a problem, you can wait until hopefully tomorrow's 10 o'clock meeting, officer, and I can do it then. You could shoot me an email, and as long as it's not too complicated, I'll try and answer your question. If you do shoot me an email, I'm not putting names on this, so I'm not embarrassing someone, although they may be from this class. The question went something like, I'm having trouble with question 4. Do you know why that's a problem for me? I don't know what section you're talking about. Is it question 4 from the first section, the third section, the fifth section? You see my problem? I need more detail. Now you can just tell me it's, you know, section 2, 3, question 4. That's totally fine. That I can handle, right? But if you do it by email, you have to be a little, pretend I'm an idiot, which is a good assumption, right? And so tell me more than you think I need, and that'll make my life a lot easier. Okay, right, let's get started. What we're going to do, we're going to do finishing off continuity, section 2.5. These are 3 questions similar to the homework, and we're going to do a thing called the intermediate value theorem, which is intuitively obvious for most people. And so sometimes when we do these questions, it's almost like you're not doing anything at all. It looks kind of weird, but it's there, so we're going to do it. Well, let's start with these fellas. A function is continuous on every number in its domain, which is essentially says, if you can find a value for a function, isn't it going to be continuous? For the types of functions that we typically deal with, and that means for these ones. So for rational functions, radicals, polynomials, things with logs in it, this statement up here is true. So let's start with the first one. If I was interested, when is this function, the one I'm writing down right now, when is it continuous? It's the same thing as saying, what is its domain? Because the 2 answers are the same. Now let's look at this guy for a minute. Isn't this function totally okay, except when the bottom is 0? You agree that's the only places you're going to have trouble. So what I would do, probably don't need to factor the top, but I'm doing it anyway, is I would factor it. And what factoring allows me to do is that it allows me to identify the 2 values of x that are going to cause us trouble. Would you agree that you can evaluate this function as long as you don't use -1 and as long as you don't use x as 8? As long as you don't use those guys, you're good. So there's our answer. Every single number except those 2. Now in interval notation, this is going to be -infinity. -infinity to -1, joined to -1 to 8, joined to 8 to infinity. If you imagine a little line with a hole at -1 and then a hole at 8, isn't this a visual representation of the values of x that you could use for that function? Do you see the 2 little holes get caused by this? It's a bit clunky, but that's what you have to type into WebAssign for your answer. We okay with the first one? Just rational functions. Just look at the bottom. What makes it 0? Don't use those guys. You got your answer. Now the second function is, where is this fella continuous? In other words, what's its domain? Right. Have you any inkling about what values can go inside a log function? You can't get the log of -2. Doesn't exist. Not as a real number. If I draw a little picture of the log function, it looks like that. So for a log function, you must be positive, right? So this guy here has to be positive. So what I'm going to do then is I'm going to say, okay, that has to be true. And now my question becomes figuring out what values this is true for. And I can visualize it. Would you agree that this cuts, I guess we'll call it the v-axis, at -1 and at 1? And would you agree that it looks something like this, right? So that guy looks like this. So when is this guy positive? Well, isn't he positive from here to here? Right? It's positive from here to here. So this is true when v is in the range -1 to 1. And that's your second answer. The domain of this function is you can only use values of v between -1 and 1. And you're not allowed to use 1 or -1 because 0, right, is not allowed, right? You can't use the log of 0. It's not an exact value. And then the last one involves radicals. Now, we're only interested in these questions in what values of u can you actually get an answer, right? And that will be the domain. And that's also going to be when it's continuous. So we're really looking for the domain here. So I'm going to do this and ignore that term. Why can I ignore this function?
It can be positive or negative.
Yeah, I can use any number I like and it'll work, right? So this one isn't causing problems. So although this question is made up of 2 parts, isn't this the only part that we need to focus on? Right, because this is the only one that's going to put some restrictions on the numbers we can use. I can plug any positive or negative number into a cube root and I'll get an answer, right? It's usable. So this is not having any issues, right? So just ignore it. It doesn't cause any problems. I'll forget you. What is true about square roots then? Well, you can't use them for everything, right? You can't do a square root if the thing inside ends up being -2, for instance, right? That's not a real number. In fact, for a square root, doesn't the thing inside have to be greater than or equal to 0? Which just basically becomes that. So as long as u is greater than or equal to half, this thing exists, and so we've got our domain. So what will our answer look like? Square bracket to infinity is how you represent u greater than or equal to 0, and that would be your third answer. Are we okay with those 3 questions? We're really just trying to find for what values of x, v, or u can you actually get an answer? And in each case, there was a slightly different result. For instance, in the last case, doesn't u have to be a half or bigger for you to be able to get an answer that you can calculate? And we call that the domain. And the domain is the same thing as when a function is continuous. At least in these questions. If this is good, I'm going to move on to the last part of section 2.5. Are we good with these 3 questions? Okay, got nods, I'm happy. Right, here's the last fella. It's called the intermediate value theorem, IVT for short. Give you a few moments to absorb it, and then I will talk about it. almost ready. Okay, here goes. What the intermediate value theorem says, I think, is intuitively obvious. They just put it in a little more mathematical way. I want you to imagine that you've got a continuous function starting at x equals a and finishing in x equals b, right? So from there to there, it's continuous. There are lots of ways of thinking continuous. Here's an analogy. If you're continuous, isn't it a single piece of string? Right, so you can travel from A to B, right? You can travel along that road, and it's one joined up function, right? Now, if it wasn't continuous, wouldn't you have a kind of hole in the ground and a break, or you get killed, right? If you try to drive along the road, right? Infinities, all the kind of things that stop you being continuous. But when you are continuous, aren't you kind of boring? You're just a single piece of string. You go from one point to the other. You drive along the road, you're fine. So if a function is continuous in the interval from A to B, then for every number you can like, any value between f of A and f of B, we're calling this value L. For any one of those numbers, it's guaranteed that you're going to be able to find a little c somewhere between A and B that has the property that the value of the function of c equals L. Right, that's the intermediate value theorem. So it's basically saying, see if a function starts at 10 and finishes at 50, isn't there guaranteed to be some place where it's 40? Like you can't get from a position of 10 to a position of 50 without passing through all the values between 10 and 50. Right? That's what the intermediate value theorem says. So what do we use it for? Well, we use it for two questions. We use it essentially to prove that an equation is guaranteed to equal 0. So this one is inversion question 20. And we're going to prove that e to the x, which is equal to 8 take away 7x, in the interval 0 to 1, right? We're going to prove that this thing has a 0, also called a root, I guess also called a solution. Right, I'll call a solution, I like that word. Has a solution in the range 0 to 1. So in other words, there's guaranteed to be one value of x where this is true. And we're going to use the intermediate value theorem to prove that this equation has a solution, right? That there's at least one number in the range 0 to 1 where this is true. So what you do is you create a function by just subtracting these guys over, which is that guy. Would you agree that this function is continuous in the interval 0 to 1? In fact, would you agree this function is continuous everywhere? But it's definitely continuous 0 to 1. Now I'm going to find f of 0. Right? That's basically my a. And what's that? E to the 0, take away 8, add 7, what's the 0? What's that? 1 take away 8, it's negative 7. Now I'm going to find f of 1. And that's e to the power of 1, take away 8, add 7. That's e take away 1. Very roughly. E take away 1. E take away 1 is about 1.72, right? Just round it off. Now you might be saying, okay, how's that going to help me prove that this is equal to 0? Because if I can prove that there's a value where this is equal to 0, doesn't that mean that this is also going to happen? Right. So, isn't this at 0? Isn't the answer -7. And at 1, is it in the answer? Up here at 1.72. Then according to the intermediate value theorem, isn't there guaranteed to be a place where the function is equal to 0? So we can just go by the intermediate value theorem. There is a C such that f of C equals 0. So a solution exists. Kind of doesn't feel like I've done anything, but what I've done is I've proved that this thing has a solution between 0 and 1. So let's show you how you do it in WebAssign. Okay, here we go. Use the intermediate value theorem to show that there is a root. I would like there is a solution, but that's fine. Given to this equation. So e to the x equals that guy, range 0 to 1, right? That's the same question, I guessed good. Rearrange it so that f of x looks like that, which I did. Right. Find f of 0, which I did. So you plug in -2. Find f of 1, which I did. And I think you go into functions. So yeah. And you go e to the power of 1, take away 1. Now, since f of 0 is less than that and f of 1 is bigger than that, we've proved that there exists a solution. So do you see in WebAssign what you're going to be doing here is filling in the value at 0, filling in the value at 1, and showing that these two guys are positive and negative, and so a solution will exist. So in this question here, you're going to do a similar thing. Right, question.
Isn't e to the 1 equal to e? So
yes.
Wouldn't you just write that? Or couldn't you just write that?
Well, what I'm worried about, and I agree with you, that's what I would want to write. I would write that. I'm frightened because I know WebAssign can be weird, that if I just hit E on my keyboard, it might not know that it's E. So the way I did it was just overkill to make sure WebAssign doesn't tell me I'm wrong when I'm really right.
Okay.
Right? That's the only reason. Now, you've got 5 shots. So why don't you hit the E on the keyboard as your first shot? And if it says, I don't like you, try E to the power of 1 version that I did and see if it likes that. So it's just WebAssign and me trying to be sure that it's going to take my answer. Okay, 21's the same guy, and that is the end of continuity section. Is there any questions about it before we start our next section? Right, they finished with a couple of weird ones, right? Intermediate value theorem is kind of sort of a weird. No questions? Okay. Our next section, 2.6. Called limits at infinity. Oh, I don't know where I am. Let me share. I'm showing you what I think I'm showing you. Here we go. Limits at infinity. So we are going to be returning to limits. And this time we're going to be looking at limits that are vertical asymptotes, limits that are horizontal asymptotes, and limits as x tends to infinity, and all the other versions of things that you could get. Today we're going to focus only on vertical asymptotes. We have actually touched on these, so this isn't totally new. if you've ever done, which you have, unless you took calculator and skipped by it, if you've done 141, haven't you done curve sketching and vertical asymptotes and horizontal asymptotes? So this is not particularly new. We're just introducing limits into the word, into the vocabulary. So here is a classic vertical asymptote at 3. And this particular function looks like that. And just looking at that picture, would you agree that the limit, the overall limit as x tends to 3 of this function is plus infinity? Does that make sense? Just visually looking at it, right? When you do limits that involve vertical asymptotes, your answers are quite limited. Plus infinity, negative infinity, or does not exist. That's the only 3 answers you're ever going to get. So your life gets a lot easier when there's only 3 answers, right? Plus infinity, negative infinity, or it doesn't exist. So what we're going to do is a kind of summary of every kind of vertical asymptote that you could get and what the left, right, and overall limit would be in each of those situations. So let's go back to that one. I call vertical asymptotes that look like that, right? The ones that go like that. I call those guys volcanoes. I don't see it in a textbook, but I like that name. Now, it look like a volcano to you? Looks like one to me. So if I talk about a function and I say, hey guys, there's a vertical asymptote at x equals 3 and it's a volcano. Do you already visualize in your head what I'm trying to tell you in English? Right. So that word is just me inventing a word so I don't have to keep drawing pictures all the time, right? So, or moving my hands like this all the time, because that's not always obvious what I'm doing, right? Now, if you look at this guy, we know the overall limit is infinity, but there are also left and right limits. So let's talk about this one. This one is the right limit, right? 3 plus. If you come in from the right-hand side, isn't the answer plus infinity? And the left limit, as you come in from the left-hand side, isn't that plus infinity? Right. Vertical asymptotes that look like this second one, right? This one here, I call them a hole in the ground. It looks like a hole in the ground, right? That's what I call them. So let's look at hole in the ground vertical asymptotes. Would you agree that the overall limit is negative infinity? Now, if you come in from the left-hand side, it's negative infinity. And if you come in from the right-hand side, it's negative infinity. And that follows a rule that we already know. For an overall limit to exist, doesn't the left and right limit have to exist and they have to be the same thing? So you see how these two are plus, that's a plus. If these two limits, the left and right, are negative infinities, that is negative infinity. If somebody gives you a picture, which they actually do in some of the homework questions, isn't it dead easy to answer left, right, and overall limit? You don't need to do much, you just look, you should be able to tell. Here's, oops, put that over here. I said there's 4. Here's the other thing. I call these guys, both of them, a one of each. It's not the best name in the world, but does it get across what's going on? If I say there's a vertical asymptote at x equals 3 and it's got a one of each, do you see a kind of up or a down? You know, you've got one of each. That's what I mean when I say that. Are we okay with that definition? Well, let's see what happens. Let's look at this one of each. Would you agree that the left limit is plus infinity and that the right limit is negative infinity? Right? Plus infinity on one side, negative infinity on the other. And because of that, isn't the overall limit does not exist? Now, in this one, they kind of very similar answers, but don't they just switch places? Isn't the left limit negative infinity? The right limit is plus infinity. So the overall limit does not exist. So far, so good. Okay. So if somebody gives you a picture and they ask you to find the limits at infinity, are we comfortable that they're pretty obvious? There's not a lot of brain work. The answer is always plus infinity, minus infinity, or it doesn't exist. Okay, so let's take that out. I'm getting nods there. I think this is pretty straightforward. Agreed? I don't think I'm doing too weird an idea. So what I want to do next is look at the same puzzle, but you're not given the picture. I'm hesitating here because I've got a window I want to find. There we go, found it. And let's jump to that window. Oh, I'm there already. Okay. Okay, that didn't work. Zoom's being a pain right now. Okay, it worked now. Okay, hopefully you're all looking at Desmos, right? So suppose you were being asked left and right limit as x tends to 2 of some rational function. They're mostly rational functions that you do these to. And you'd like to know left and right limit. Couldn't you simply just go to Desmos, which I'm about to do, and type in the function? So let's suppose the function is x over x minus 1 close bracket squared, and do an x plus 1. Right. Now, do you see what you get is a very nice picture of what the heck is going on? Okay. Now, if I just, I don't know if I want to shrink it or scale it. It's hard to do. I guess if I do that, you see the vertical asymptote better, but it's kind of hard to read off the positions. So I'll do a little compromise. How about that? Right. Can you pretty much see everything you need to know in that picture? So let's look at x equals 1. Do you see a volcano here at x equals 1? Great. So wouldn't the left limit as x tends to 1, the right limit, and the overall limit, wouldn't all those answers be plus infinity? Agreed? So if you had this function and you wanted to know what the limit is, x tends to 1, x tends to 1 minus, or x tends to 1 plus, wouldn't your answer be plus infinity in all three cases? It's in front of us in that picture. How about at the negative 1 position, right? There's a vertical asymptote here. Trying to share the thing. Isn't this a 1 of each shape? Okay. What is the left limit as x approaches negative 1? The left limit.
Infinity, positive.
Agreed. The right limit.
Negative.
Right, it's negative infinity. So what's the overall limit going to be in that case?
Does not exist.
Right. So these questions are not going to tax your brain power. Would you agree? If they give me a picture, bingo. If they don't give me a picture, nip over to Desmos and make a picture, right? So what's the third thing that they're going to do to you? They're going to tell you not to use a graph. And the temptation will be to use a graph. But you're going to have to do a table of values. So let's just do it, bite the bullet and do a table of values and show you that a table of values can also be used to answer those same questions that we just did there. So I'm going to have a function. It's going to be that guy. 3 over x minus 2 cubed. Now, it's pretty obvious here. Would you agree that there's a vertical asymptote x equals 2? And they'd probably tell you that anyway. But we want to know 3 things. We want to know, using a table of values, what the overall limit is. And we also want to know what the left limit is. That's a minus there. And actually make that the right limit. That way I can do a better version of the left limit. So you want to know a left, a right, and an overall. The easiest way would be, wouldn't it, to plug in any Desmos and see what you get. Right? Do you get a volcano? Do you get a hole in the ground? Or do you get one of each? Because once you've done that, isn't the plus and minuses going to come naturally? But let's show you how you would do it with a table of values. Since I'm interested in 2, I'll start with the small side, right? The left-hand side. 1.9, 1.99, and finally 1.999. And then the other side, how about 2.1, 2.01, and then 2.001. Do you see that I'm approaching 2 from the left and from the right? So that's the set of table of values I would use. Now, they may give you in WebAssign the numbers that you're going to use. So they may give you, 8 numbers, whatever they ask you, use them, right? But these are the ones I'm picking, right? Now, I want to find the value of this function at these points, and then I'm going to use this table to answer these questions. So, let's do it with a, no. Do you want me to do it on this hand thing, or do you want me to see it in the big calculator? Because some of you, I think the big calculator is just easy to see what I'm pressing. Which I'm going to do the table, but which one do you want me to do it on? This thing in my hand, or do it with the software? Do you care?
Anything's fine.
Okay, well, I'll do this thing, right? Because it's less hassle for me. Right, let's clear this out of the way. Let's clear this out of the way. Let me just, you don't need to do this. I'm just going in and making sure that my calculator is like clean and doesn't have leftovers from another question to confuse everyone, including me. So you go and you hit y equals, and you type in whatever the function is. So 3 divided by a bracket, x take away 2, close the brackets, to the power of 3, got it in. Second table, I go down here and put it into ask, and then I go second table. And I type in 1.9, 1.99, 1.999. Only one of those answers fits. Do you know -3e to the 6 is just -3 million? You know, that's just -3 times 10 to the 6. Right? And isn't this one -3e9, -3 times 10 to the 9, right? -3 billion. So can I just say -3 mil and -3 bill, and you know what I'm talking about? Right, let's just pause there for a minute. That tells me something. As you approach 2, and this is from the left-hand side, so this is a left limit, isn't the answer getting infinitely big and negative? Are you comfortable about how this table of values tells me this is going negative infinity on me? Okay. Now, let's do the other side now. 2.001, 2.01, and finally 2.1. And if I put these numbers in, I guess I'll do them in green just to be different. I get 3,000. Oh, it's very symmetric. 3 million and 3 billion. Whoa. If you're coming in from the right-hand side, isn't the answer getting bigger and bigger, but positive infinity? Now, when you put those two together, what conclusion do you have for the overall limit then? If this is negative infinity and this one is plus infinity, what's the overall limit?
Does not exist.
Right. You agree on that? Yeah. Okay. I'm going to go to Desmos now. And I'm going to type in 3. Oh, I guess you should see me doing it. Okay. I'm having button pressing issues. Here we go. Gotcha. So it's 3 over, I'm assuming that you can see it, x take away 2 close bracket. No, try it again. X take away 2 close brackets. I want it to the power of 3. So okay, so to the power of 3. Would you agree the left limit is negative infinity, the right limit is plus infinity, and the overall limit does not exist? Isn't that a classic one of each? So if you didn't have a graphing calculator or access to Desmos or any of those other things, and won't a table of values get you the same result? It just takes you, a little bit more work. Again, I'm getting good vibes off this one. I like good vibes. Are things so far intuitively make sense to you, right? You want to find a limit on a vertical asymptote. You can do it as a picture. If you're really stuck, probably you won't want to, but sometimes they make you. You could do a table of values, right? I'm now going to show you a third way of that same answer. And this technique uses a concept called infinitesimals. God, that's a mouthful. Infinitesimals, right? Now, these are special numbers, and they use a notation that looks very like, what's that? That should be a 2 there. Like 2 plus and 2 minus. In fact, 2 plus and 2 minus are examples of infinitesimals. So if you write down 2 plus, nothing to do with limits, just 2 plus, right? What you mean is it's a number that is equal to 2, but a tiny bit bigger. And tiny means really tiny. It means like 2 trillion zeros and then keep doing some more zeros after that and stick a 1 at the end, right? So it's like a 2 point, write zeros till you die, and then just before you die, stick a 1 at the end, right? Whatever way you want to do it. That's how tiny 2 plus is. It's infinitesimally different, right? Infinitely small difference. Now, for completeness sake, won't 2 minus be the same thing, but a tiny bit smaller? So won't a 2 minus be like a 1.99999 till you get tired of saying nines? Now, I'm going to do a calculation with a very special infinitesimal. And the one we're going to deal with is 0 plus and 0 minus. So can you imagine what 0 plus is? isn't it a number that's almost zero, but it's still positive? Because isn't it 0 point, lots of zeros and a 1? It's still positive. And won't the infinitesimal 0 minus be roughly 0, but won't it still be negative? So 0 minus would be like negative 0.2 billion zeros and a 1, right? It's still basically 0, but isn't it just a little bit small, right? Now, here is a calculation. And this is eventually going to get to this, right? But we take a little bit of time. Here is a calculation with an infinitesimal in it. Now, if you take a number 3 and you divide it by 0, don't you get some kind of infinity? But the problem is, if I put 0 in, I don't know which kind of infinity I'm going to get. Because technically, couldn't it be a plus infinity or a minus infinity? You can't really tell unless you look at the graph, right? But in this case, can't you tell that the answer is going to be negative infinity? On the other hand, won't that guy, and I'm emphasizing it because you don't normally put plus in, but wouldn't that guy be plus infinity? Okay. Right, now that you got the background, I'm now going to use that to find out what that guy looks like. Now, if I want to find the limit as x tends to 2 plus of this function, 2 plus is my infinitesimal. So I am going to go 3 over 2 plus, take away 2 cubed. Now things get a little bit tricky, but let's see what they look like. If you take 2 plus and you subtract the normal number 2 from it, isn't 0 plus left? Isn't it an infinitesimal that's just slightly positive? Right, because that's 2 point, a lot of zeros and a 1, and then you take away 2, so what do you get? 0 point, a lot of zeros, right? So that is 0 plus cubed. Now, suppose you take the infinitesimal 0 plus and you cube it. What infinitesimal do you get out of that? So you take it, yeah. Now, what does 3 over 0 plus get you?
Positive infinity.
And wasn't that the answer that we got from our table of values? Does that notation begin to make a little bit more sense once you realize that's just an infinitesimal? Now, for completeness sake, let's do the 2 minus 1. Then shouldn't that be 3 over 2 minus, take away 2 cubed? Okay, if you take a number that's slightly less than 2 and you subtract 2 from it, don't you get a number that is negative 0, right? A 0 minus, right? An infinitesimal that's negative. And if you cube a negative, don't you still get a negative? And doesn't that guy get you negative infinity? So if you wanted to find the limit of a vertical asymptote, I think most people would just say, give me a graphing calculator. I just want to look at the picture and do it that way. You probably would say, I don't want to do a table of values, take too long, but if you make me do it, I'll do it.
So if it was squared, would you change the sign?
Yes. Suppose it was a different question and it was a 0 minus, but it was squared. Doesn't an infinitesimal 0 minus, when you square it, become the infinitesimal 0 plus? And in that question, wouldn't the answer be plus infinity? Kind of cool. Just a different approach to finding a limit. You don't need to do this. You're never going to be asked in WebAssign to do this, but it's kind of a useful addition or way to look at it, I guess. And that is us for today. So bye.